Okay, so last tutorial we added the collisions between objects and it works pretty well, as you can see here. However, I am going to be adding a couple more features to this functionality. First, I'm going to be adding a mass to each of the balls, and then with the mass, I'm going to be able to calculate the exact ratio of movement for the balls so that the balls move accordingly if, let's say, one of them is heavier than the other. And I'm also going to be adding an elasticity attribute to the balls so that you can control whether or not the balls bounce, the amount of energy that's conserved, and yeah. So let's get started. So first off, let's just go to the ball, and for this we're going to be doing this dot mass equals mass, and this dot inverse mass equals a ternary operator, and we're just going to put mass over here. This is going to be in kilograms, I guess. Actually, we won't worry about units. Let's just put it as that for now. So then the inverse mass will be a ternary operator that checks whether or not it's greater than 0. If it's greater than 0, return 1 over mass. Otherwise, just return 0, because dividing 1 over 0 is going to be, it's going to result in an error, so that's what we're going to do for this. Also, let's add an elasticity equals elasticity. Let's define it over here. And let's set it to 1. 1 means 100% of the energy is conserved. 0 means none of it. 0.5 means half of the energy is conserved in the collision. Now let's go and edit the code that we had previously. So this method does not have to change because it does not use anything related to mass, so we don't have to touch that. However, resolve ball penetration and resolve ball collision do. So let's get started with those. So over here we're going to be changing the penetration resolution, and initially we put it as divided by 2 for this as the multiplication. However, if we are considering the masses, this must be different. So instead of this, we're going to be doing this. This dot inverse mass plus ball dot inverse mass. And so this is done because in the equation, in the real physics equation, this is what we have to do so that we can get the penetration resolution, or the velocity. And so over here, what we would do is we'd multiply this by this dot inverse mass, and we'd remove this and multiply by ball dot inverse mass. So now this accounts for the ratios of the mass. Now let's move to resolve ball collision. So the relative velocity could stay the same. However, the new separating velocity has to change. And this is what I was talking about earlier, how we're going to be using this later, because it makes it much easier. So we're going to be doing this, math.min, this dot elasticity, and ball dot elasticity. So it chooses the lowest elasticity between the balls, so that it uses it to multiply the new separating velocity. And this new separating velocity is essentially VF. This is VI, this is VF. And essentially it's used to calculate the impulse by using its difference. So calculate impulse, separating velocity difference equals new separating velocity minus separating velocity. I believe we don't need this anymore. We can remove that. And instead, we are going to be calculating the impulse, which is the separating, oh, I misspelled it, of course. here as well. And then the impulse is just the separating velocity difference. I'm going to remove this. Yeah, it kind of gets a bit confusing when you have these many words. But, so that's that. And then we essentially do the same thing as what we did before. This dot inverse mass plus ball dot inverse mass. And then we calculate the impulse vector, which goes in the same direction as the normal, not the unit normal though. And then we multiply it by impulse, like that. And then this dot velocity equals, we have to change this. We have to change it to impulse vector dot multiply. And again, this is the ratio that I was talking about earlier, and it's going to account for the masses, the differing masses. There you go. So now, if everything's correct, it should work. It still works normally. But now, let's say we change the elasticity to 5.5. Yeah, see, they stick to each other. And if it's super elastic, let's say 3 times more elastic. Yeah, there you go, see? It's kind of like an explosion that happens. Right as it hits, an explosion happens and it bounces. And so you could change the mass. Let's say the first ball, the one that we're controlling, we could put it as 10. We'll set the elasticity back to 1. And you can see that this one's 10, right? This one, we set that as 10. I seem to have found the problem. We have to put this as ball dot inverse mass. And so, yeah, see over here as well. So now if we test it, there you go. The second ball moves much faster. And so one last thing before we leave, I just want to check whether or not the momentum is being conserved throughout both of the balls. So let's just console.log ball1.mass times ball1.velocity.magnitude plus ball2.mass times ball2.velocity.magnitude. And let's just put this as a fixed number so that there's not too many decimal places. Also, we need to go onto the ball and set the friction to 0 just so we can make it a bit more visible. So as you can see, it shows the total mass times velocity of the system. And so right now it's 40, the value is 40, now it's 28. So if they collide, it should be conserved. So see, this one goes slower, but the other one goes faster, and so it ends up being the same as before. Over here, it just shows a decimal. That's because it's during the collision. Otherwise, it's conserved. And so we have elasticity working now. So it's pretty sick. We're almost done the physics engine. Now all we have to do is just add walls, and we could add the bounds for the canvas so that they don't bounce around and go out of the screen, as you can see over here. And then that's essentially it, I think.